For example, 1a, we're asked to graph f of x equals square root of x. This piece I've already done for you because that was from section 2.2. So in section 2.2, we did our square root function. We put in 0, 1, and 4 to give us nice whole numbers back. And that gave us y values of 0, 1, and 2, which gives us this graph here for the square root of x. We're also going to graph g of x equal to the square root of x plus 3. Notice the plus 3 is on the outside of the radical. And then we're going to graph h of x equals square root of x minus 5. Again, minus 5 is also on the outside of the radical. So we're going to graph all three of these on the same coordinate plane, and we're going to compare. What we're trying to determine is how does adding a constant or subtracting a constant on the outside of the function affect the graph. The function g of x equals square root x plus 3. If we put in 0 for x, you should get 3 back. If you put in 1 for x, you're going to get 4. If you put in 4 for x, you're going to get 5. So let's plot those points. We've got ordered pair 0, 3, ordered pair 1, 4, and 4, 5. Okay, so can you see what's happening to that function? That original graph is the same shape, but it's in a new position. It's been shifted up. How many spaces has it been shifted up? And you've got some fill in the blanks that you can answer. In our notes, it says adding 3 to the original function shifted its graph blank units in what direction? So you can see that it's been shifted up. It's been shifted 3 spaces, and you can say an upward direction. What happened with the h function? So let's go back to our t-table. We'll do the same x values. If you put in 0 for x and h of x equals square root x minus 5, you're going to get a negative 5 for y. If you put in 1, you're going to get negative 4. And if you put in 4, square root of 4 is 2 minus 5, you're going to get negative 3. So let's find these points. 0, negative 5 is here. Ordered pair 1, negative 4 is here. And ordered pair 4, negative 3 is about right here. Connecting these points, we've got the same shape. Mine should be a little bit flatter. Like that. Okay? We've got that same shape. This time it's been shifted down. And let's go ahead and label it. We've got this was h of x equals the square root of x minus 5. Alright, in our red graph was g of x equals square root x plus 3. So how can we answer the questions pertaining to the h of x function where we're subtracting 5? What's happened to the graph? Subtracting 5 from the original function shifted its graph how many spaces or how many units? It started at the origin and it went down 5 units, and it was shifted in a downward direction. So as you can see, adding a positive number on the outside of the function is a vertical shift. If it's a positive number that you're adding, you're going to be moving it upward. And if you're subtracting or adding a negative number, you're moving it downward. And if you're subtracting 7 from the original function, then you're just going to move the original graph down 7 spaces. Example 2, we're given 3 functions to graph. This time, we're starting out with the original square root function, just like we did in example 1 part A. But instead of adding and subtracting to the outside of the square root like we did before, this time we're putting changes on the inside of the radical. So as you're writing this down, be really careful that this time you should be extending the radical, the square root symbol, beyond the addition and subtraction of your constant. So all the changes are inside the square root. What is this going to do to our equation, or to our graph? You can start by putting in values for x that will give you nice numbers to work with. And again, we've already done the square root of x. We know that it's going to go through, we can do 0, 0, 1, 1, and 4, 2. Which is about right there. So we have put in 0, 1, and 4. And then our y values came out to be 0, 1, and 2. So that's how I'm getting my graph for the square root of x. Okay? Now we need to see what happens in the second one. How does subtracting 3 on the inside affect it? We'll do another t-table here. Now this time, when you go to substitute in these x values that you used before, they may not work out as well. If you put in 0 for x into your g function, you're getting 0 minus 3, which is a negative 3 on the inside of the radical, and that's not going to give you a real answer, a real number back. So we're going to have to think about values of x that we might want to put in here that will give us both numbers that are easy to work with and also legitimate whole numbers, or excuse me, real numbers. So what would be a good choice to put in here? Maybe you could put in, let's try a 3. We could try a 4. And maybe we could try a 7. Now, how did I choose those numbers? It might seem like I just pulled them out of thin air, but I'm trying to find numbers that if I put in for x, I'm going to get something nice that's easy to work with when I subtract 30. So you can go ahead and substitute those values of x in and fill out the y values in the table and plot those points. And then we'll come back and look at it and then continue with part H. So when you put in 3 for x, you should have gotten 0. When you put in 4 for x, you should have gotten 1. And when you put in 7 for x, you should have come out with 2. So let's find these ordered pairs. We've got 3, 0, 4, 1, and 7, 2. And I'm going to have to move that because it's kind of in the way. So 7, 2. Okay, so here is my new graph. What's happened to the original graph? Notice it has been shifted, and you may have fill in the blanks here to fill in. Yep. So in your notes, we've got that subtracting 3 from x under the radical shifted the original graph. How many spaces? It went 3 spaces, and it got shifted in what direction? It moved to the right. Okay. So this was the g of x graph. And this was original f of x. So for h of x, we need to put in values for x that will give us easy, nice numbers to work with. In other words, what values can I put in here for x that are going to give me positive numbers under this radical, and also it's nice if they're whole numbers and not decimals. So, for example, a negative 5. If you put a negative 5 in here, you're going to get 0, and you can take the square root. So put in negative 5 for x. Maybe a negative 4. And what else would be a good one? How about a negative 1. I think these are going to be good numbers. So try those and see what happens. So when you put in negative 5 for x, you're getting 0. If you put in negative 4, you're getting 1. And if you put in negative 1, add 5, that gives you 4. Take the square root and you get 2. So these are the ordered pairs that we want. Negative 5, 0. Negative 4, 1, negative 1, 2. And I can connect these dots. So what's happened to the original f of x equal to the square root of x when I added 5? believe you've got to fill in the blank in your notes. No, you don't for this part. Okay, yeah, you do. I'm sorry. So at the very bottom of the page, you've got adding 5 to x under the radical, shifted the graph, and my dots are not quite right, but shifted the graph, it went 5 units, and it went to the left. Okay, so this is the horizontal shift. And we've got the definition: a horizontal shift occurs when we add or subtract a value from x. In other words, if you add or subtract on the inside of the function, so if you're working with the square root function, that means that you're adding or subtracting a number from the x inside your square root. It might also occur, you might add or subtract a number from x inside an absolute value function, for example. Or you could be working with the x squared function, and you might add or subtract from x, and so you would have maybe x minus 2 in parentheses quantity squared. That would also be a horizontal shift. There's another thing that's important to notice about your horizontal shifts. If you look at g, function g, we subtracted a constant, and our function did move horizontally 3 spaces, but it went to the right. And then over here in h, when we added a positive number inside the radical, that moved the function to the left 5 spaces. So the direction, the horizontal shifts, the number tells you how many spaces to move. The number that you're adding to x tells you how many spaces, but the direction seems backwards from what you're going to expect it to do. We saw with the vertical shift, adding a positive moved it up, adding a negative moved it down, and that makes intuitive sense. But you're going to have to remember that the horizontal shifts are not quite that way. Adding a positive will move it to the left, and then adding a negative will move it to the right. So they're going to seem a little bit backwards. For example 3, we're asked to graph each pair of functions on the same coordinate plane. Part A, we're going to graph f of x equals x squared and g of x equal to negative x squared. We already know the graph of x squared. We're familiar with that one. We can generate it very quickly. We know that these x values are really good ones to start with. Putting these x values in would give us back y values of 4, 1, 0, 1, 4. And we can quickly find that. Plot these, negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, positive 4. All right. Again, how do you connect these dots? You look at the type of function you have. This is an x squared function. They need to be a curve, not definitely not straight lines. So we're going to connect these, creating a parabola centered at the origin. So that's our x squared function. All right. So this is f of x. All right. Now we need to do the graph of g of x equal to negative x squared. Basically, what happens by putting the negative in front of the entire function? How does that affect our graph? So let's come back to our t-table. We're going to put the same x's in. I'm going to let you think about what the y value should be. So I'd like you to pause for a moment, fill in your t-table, and then think about what's going to happen to your graph before we continue. So your y values, you should have gotten negative 4 here, because if you put negative 2 into this for x, you've got this negative sitting in the front. So you've got a negative parentheses, and you're putting in a negative 2 and squaring that. So you're going to square your negative 2 on the inside. Negative 2 times negative 2 would give you a 4, but this negative in the front still stays there. So you've got negative 4 here. Putting negative 1 in for x, the same similar thing is going to happen. You're going to get a negative 1 back. Putting in 0, you'll have 0. If you put in 1, square that, you get 1, but you still have that negative that sits in the front. So you'll have a negative 1 and a negative 4. What is that going to do to our parabola? We've got negative 2, negative 4. Negative 1, negative 1, 0, 0, 1, 1, and 2, negative 4. Okay, so what's happened to our parabola? Putting that negative in front of the entire function has flipped it across the x-axis. This is what we call a reflection across the x-axis. Okay, so the original graph has just been reflected across the x-axis, and it's created a mirror image down here. This is f of x, this is g of x equal to negative x squared. Example 4, we're asked to graph on the same coordinate plane for part A, f of x equals square root x, g of x equals 2 times the square root of x, h of x equals 1/2 times the square root of x. So here we're going to see how multiplying numbers in front of our function will affect our graphs. Here let's notice that we're multiplying the original square root function by a number larger than 1. Over here, we're multiplying by a number that is smaller than 1, but still positive. So we're not interested in this example about negative factors or negative numbers. We saw what happens in the previous examples. If you multiply a function by a negative, we know it's going to flip it across the x-axis. But here, we're just looking at positive numbers, but we're going to compare what happens multiplying by a number larger than 1 versus multiplying by a number smaller than 1, or between 0 and 1. Okay, so I've graphed the square root function. We've been through this multiple times now, so you should be clear on that. These are the numbers that I put in. I put in 0, 1, and 4 for my x's, and then I've got 0, 1, and 2 back for my y values. So now I'm ready to do the g of x function. I'm going to put in the same x values. If I put in 0 here, square root of 0 is 0, and then I have to multiply it by 2, but that's still 0. So I still get the 0, 0 in front. If I put in 1 for x, square root of 1 is 1, and then multiply by 2, so that gives me 2. And if I put in 4 for x, square root of 4 is 2, and multiply by this 2, I'm going to get 4. So how is that going to affect the original square root graph? We've got ordered pair 0, 0, 1, 2, and 4, 4. This is what we call a vertical stretch. Okay? What has happened is, if you can imagine grabbing hold of your y-axis and just pulling it so that the original function is just getting stretched vertically. So it's resulted in it coming up higher like this. So now it's coming up this way. Anytime we multiply our function by a number that's greater than 1, we will have some type of vertical stretch. The larger this number, the more it's going to get stretched. So if we had a 10 sitting out here, then it might have gone up like this. Okay? So again, the vertical stretch comes from multiplying the function by a number larger than 1. All right, let's look at h of x. What's happening here? We're going to multiply by a number smaller than 1, but still positive. So coming back to my t-table, I'm going to put in those same x values again. If I put in 0 for x, take the square root of 0, I get 0, multiply by 1/2, and I still get 0. If I put in 1 for x, take the square root of 1, I get 1, multiply by the 1/2, so I get 1/2. If I put in 4 for x, take the square root of 4, and I get 2. 2 times 1/2, it gives me 1. Okay, so we'll plot these points, and our h of x graph, we'll see where it's going to be. So we've still got the 0, 0. We've got 1, 1/2, and we've got 4, 1. All right, you can think of this one as a compression, a vertical compression. If you again grab hold of the y-axis, and this time you're going to squish it this way, it's going to flatten it out closer to the x-axis. All right, so that vertical compression occurs anytime we multiply our function by a number smaller than 1, but still positive. Okay, in the notes, let's take a look at your notes for a moment. We've got a definition. So just before example 4 in your notes, The definition states that the graph of y equal a times f of x is obtained from the graph of y equal f of x by first stretching the graph of y equal f of x if a is greater than 1, or shrinking, which I refer to as the vertical compression. You can think of it as squishing it. Shrinking the graph of y equal f of x if a is less than 1, but it still has to be positive. Okay, again, what happens if you multiply your function by a negative? It would get flipped across the x-axis. That would be a reflection. For example 5, we're asked to apply what we've learned involving transformations to graph our equations. We are not going to be doing a t-table this time, and I'm not going to use a graphic calculator because I don't need it. And you should be able to do it without a graphic calculator as well, because once you understand these steps, it's pretty straightforward about how to proceed. In your notes, you need to look over the order of steps that you should follow to graph an equation like this. So in your notes, right before example 5, it says to graph y equal a times f of x minus h plus k. That's just saying that if you've got a function that involves a horizontal translation, or a vertical translation, or stretching, or shrinking, etc. You follow these steps. You first do the horizontal translation. You second do your reflecting, stretching, shrinking, etc. And then you finally do the vertical translation last. So that's what we're going to do here. The first thing we need to do is decide what is the parent function that we're working with. What is all of this based on? In other words, is this an absolute value equation? Is this a square root function? Is this a cube root function? Is it a cube function? Which one is it? Well, we've got this square here, so we know that our parent function is x squared. Is the y equal x squared graph. And we know what that looks like. It's a parabola centered at the origin. So I'm going to use a dotted line to draw it in. Okay. So that's our starting point. We know that we need to do the horizontal translation first. Where do we find the horizontal translation? That comes from the inside here. This minus 3, you see that you're subtracting 3 from your x on the inside of the square function. So that tells us that we need to shift the graph, and do you remember what to do here before I tell you? The minus 3 is telling you to move the graph horizontally 3 spaces. So you're going to go to the right 3 spaces. So you're going to, and again, remember the horizontal translations are opposite of what you want them to be. If you're subtracting, you need to go to the right. So we're going to move that origin over, or excuse me, we're going to move that vertex over 3 spaces to the right, putting us here. So I'm going to draw another dotted one here. And of course, these are parabolas because they're x squared function. All right. Next, we need to apply any reflections, stretching, or shrinking that needs to be done here. This negative 2 is actually 2 things. The negative is, what is the negative out here telling me to do? That negative is telling me to reflect this across the x-axis. The negative 2 is telling me to stretch it and also bring it in closer to, if it were the original one, we would be bringing it closer to the y-axis. But we're going to be bringing it in closer to this vertical line now going through the 3. So we're going to stretch and reflect this. So it's going to be a skinnier version of what you have here, turned upside down, so like this. So you've got it should be about half the width. Last step is the vertical translation. So we need to move this out here, this plus 4. What does it tell me to do to it? That tells me to move it up 4 spaces. So I'm out of color, so I'm going to, what color should I use? Maybe I've got some. I've got a purple. I don't know how it's going to show up in the video for you. But my final answer is going to be what I've drawn here, but it needs to be shifted up 4 spaces. So it needs to come up here, and I can draw it as a little bit of a skinnier graph like that. So that's my final answer. My vertex is at the point 3, 4. And it's a parabola that opens down. I have not found my x-intercepts, but they're roughly around x equal 2 and x equal 4, but maybe not exactly. I'm going to be interested in certain types of symmetry, working with graphs. These two graphs are examples of symmetry with respect to the y-axis. If you have symmetry with respect to the y-axis, that just means that if you were to take this graph and imagine if it's on a piece of paper and you fold it down the y-axis, so these two sides come together in the middle, anything on this side and anything on this side need to be touching when you bring them together. You could also think of it as if you were to take the entire graph and flip it around, would it give you the same picture back? And this one would. You should know what this graph represents, which function that is. This is y equals the absolute value of x. So this one has symmetry with respect to the y-axis. This graph also has symmetry with respect to the y-axis for the same reason. Granted, my drawing is not perfect, but this graph, the function for this graph does have symmetry with respect to the y-axis. And again, you should know this by now. This is y equals x squared. It's the x squared function. It has symmetry with respect to the y-axis. Now there's only two, well for right now there's only two types of symmetry that we're really interested in. Symmetry with respect to the y-axis and symmetry with respect to the origin. We're not that interested in symmetry with respect to the x-axis. I'm not going to say why right now. It might be that would be a good extra credit question for me to ask you later though. Why are we not interested in symmetry with respect to the x-axis when we're working with functions? Okay, I'll let you think about that. We are interested in symmetry with respect to the origin. These two examples, or these two graphs, are examples of symmetry with respect to the origin. What happens with these? One way that you can think about this is if you were to take this picture and rotate it 190 degree and then another 90 degrees, so you're going to turn it upside down. And if it gives you the same picture back that you started with, then you have symmetry with respect to the origin. This one you need to be able to recognize. This is y equals x cubed. Okay. And then this one over here, same idea. If you take this entire picture and you rotate once and one more time, so you turn it upside down, you get the same picture back that you started with. This one we've not worked with much today at this point, but this is y equal the cube root of x. But it is one that you are responsible for being able to recognize. Both of these have symmetry with respect to the origin. In your notes, you'll find a definition for even and odd functions. I'm not going to read through the definition, I'm just going to talk about it with you. An even function is any function that has symmetry with respect to the y-axis. So for that reason, y equal x squared, y equal absolute value of x, we just looked at their graphs and saw that they had symmetry with respect to the y-axis, so they would also be called even functions. An odd function is a function that has symmetry with respect to the origin. You'll notice that I'm abbreviating WRT, that means with respect to. So based on what we just saw with our graphs, we saw that the graphs of y equal x cubed and the graph of y equal cube root of x, both of those were symmetric with respect to the origin, so both of those are odd functions. Again, there is no special category for a function that has symmetry with respect to the x-axis. That's something I would like you to think about as to why. We want to look at the definitions for even and odd functions. We're going to use this information to help us determine algebraically if an equation, or excuse me, if a function is even, odd, or neither. It's one thing to do it from the graph, and if you have the graph to look at, it's very helpful. But we also need to be able to do it algebraically. So we have, this is in the notes just below the examples of symmetry graphs that we were looking at. We have the definition: if f of negative x equals f of x for every value of x in the domain of the function f, then f is called an even function and its graph is symmetric about the y-axis. So the f of negative x equal to f of x, what does that mean? That means if you put negative x in place of your x in the original problem, and you get the same y values back, so your y's are still the same, then that would be an even function. Another way you could think of that is if you put in negative x for x, you need to get the same thing back as you started with. So you're checking to see if you're getting the same exact equation back by substituting negative x's into the original function. All right. Our second definition: if f of negative x equals negative f of x for every value of x in the domain of the function f, then f is called an odd function and its graph is symmetric about the origin. So here you're substituting negative x for x, and all of the y's are coming out to be opposite signs. Another way that you might want to think about this one, when I do it, I'm going to put in negative x and negative y into the original function and see if that gives me the same thing that I started with. To me, it's a little bit easier to check it or to test it that way. So look, we are ready to look at example 6, I believe. Yeah. So we get to use these techniques in example 6. We are asked to determine if the function is symmetric with respect to the y-axis or the origin. Also, is the function even, odd, or neither? Okay. I just wrote up here, is the function even, odd, or neither, because that's the same question as asking if it's symmetric with respect to the y-axis or with respect to the origin. Remember, even means symmetric with respect to the y-axis. Odd means symmetric with respect to the origin. So that's what we're testing for here. All right, so in part A, I want to see, let's first check to see if this is even. Let's see, I'm going to get rid of this and make a little extra space. So is the function even? Or is the function symmetric with respect to the y-axis? My rule tells me to substitute negative x for x. If that gives me the same thing as my original equation, then yes, I can say it's symmetric with respect to the y-axis. So I'm first going to rewrite this. I'm going to drop my function notation and just write y. And then I'm going to put negative x for each x. Like that. And then I'll use order of operations to simplify this. Okay, if I cube my negative, it's still negative, so I can read my negative out. I'll have negative 5x cubed. And here my double negative cancels and gives me a plus. So is negative 5x cubed plus x the same as what I had up here? Do they match? They do not, because I've got a minus and a plus. So this is not even. And it's also not symmetric with respect to the y-axis. Is f of x equal 5x cubed minus x odd? In other words, is it symmetric with respect to the origin? So we want to substitute negative x for x and substitute negative y for y. So we'll have, if you want to rewrite this and just drop the function notation, you could just think of that f of x, that's just y. So we're going to put negative y, and we're going to put in negative x. Okay, we're going to simplify and get this solved for y again, and then we can compare. Again, a negative raised to an odd power will still be a negative, so it's going to be negative 5x cubed, and then this is going to be plus x. Alright, solving this for y, I need to, you can think of this as dividing both sides by your negative 1, so you'll change all the signs. You'll get positive y equals positive 5x cubed minus x. So we want to compare this equation with the original equation here. Do they match? They do, yes. So we can say yes, this one is odd, and it's also symmetric with respect to the origin. So testing for symmetry with respect to the origin is the same thing as testing to see if your function is odd. You're doing two things at once. Our last example from section 2.3. You can be very excited that this is the last one because this one has run on rather long. We're asked to solve the inequality by graphing. You can do this on the calculator to help you. I'm going to just go through what we've discussed today and show how to do it by hand. If you were asked this question on a test, you do have to show some work. You need to show the steps that I'm going through, but I certainly encourage you to use the calculator to check yourself. So we first need to know, what does this graph look like? We need to ask ourselves, what is the parent function? Well, we've got this quantity x minus 1 squared minus 2. So my parent function is going to come from the x squared function. What does that tell me? That tells me I'm working with a parabola. And then I can do my transformations. There's only two things going on here. We've got the minus 1 inside the parentheses, which we know is a horizontal shift, so it's going to move our parabola one space to the right. So we've got here's the original parabola. We're going to move it one space to the right. Bring it here. And then the minus 2 is telling me this is my vertical translation. I need to move it down 2 spaces. So that puts my vertex over here at order pair 1, negative 2. And I know I've got a parabola going up like this. So if I were to sketch it, I could sketch it without all of the information just yet. But I do need to know a little bit more information. Okay, so I know that I've got a parabola that opens up, and the vertex is at 1, negative 2. I know it does something like this, but I need, we're being asked to do a little bit more than to just graph it. We're asked to solve the inequality. So what does that mean? If all this is less than 0, okay, well, you can think of this entire function on the left side as like your y value. So if the y is less than 0, where does that put us in terms of the graph? We are being asked, when does this graph dip below the x-axis? When is it this piece down here? So we can see that our answer is coming from the graph being below the x-axis. And again, it's because we're being asked, if you think of all this as the y, when is the y less than 0? So when is the y negative? When is the y value under the x-axis? So our answer is coming from this portion of our graph. All right, but before we can actually state our answer, we need to know where the boundaries are here. We need our x-intercepts. I don't think we've talked about how to find x-intercepts before, but I know you've done it in the past. To find your x-intercepts, you need to let your y, well, let's just take a look at this. Now, I've drawn a picture of it. This is probably not exactly accurate because it's just a freehand sketch. But based on what I've drawn, it looks like I would have an x-intercept right here when x is negative 1, because that's when the y is 0. So if my function is touching the x-axis, that means that my y value is 0. So I can use that to help me find my x-intercept. So to find the x-intercept, we need to let y equal 0 and solve for x. Well, if y equals 0, that means you're going to take all this and set it equal to 0 and solve for x. So that's something that we can do. We've talked about that. So we're going to say x minus 1 quantity squared minus 2 equals 0. And you can solve this. That's just a quadratic equation now. You could do the square root property. You could do the quadratic formula. You could factor it. You could complete the square. This one is set up nicely to do one of those methods. My choice here would be the square root property, because we've already got this perfect square, x minus 1 quantity squared. I'm going to add 2 to both sides. and then take the square root of both sides. So you'll have x minus 1 equals plus or minus the square root of 2, and add 1 to both sides, so x equals 1 plus or minus the square root of 2. Now, because I'm looking at this in terms of a graph, that's kind of hard to graph in that exact form. So let's get the decimal approximations for that. The decimal approximations would be, this would be approximately, x is approximately 2.41, or x is approximately negative 0.41. Okay, so those are my x-intercepts, 2.41 and negative 0.41. Now, did I get that about right? Nope, I'm way off. So I can draw this a little bit more accurately now. Negative 0.41 is about right here. And 2.41 is about right here. I'm not too far off. So my graph looks like this. And I'm ready to give my answer. All right, I'm going to be using interval notation to give my answer. Okay. So I know that the answer is when the graph is dipping below the x-axis, so it's all the x values from here at negative 0.41 up to positive 2.41. So I'm going to give that as an interval. So my solution to this, this entire this function is less than 0 on the interval from negative 0.41 to positive 2.41. So I'm giving the x values for when this function dips below the x-axis. So it's all the x values from negative 0.41 comma to positive 2.41, and that is my answer. If you don't understand any of this, the graphing calculator can help you as well. If you go to the y equals button, and I can pull this up in the classroom on the computer screen and show it to you. But if you go to the y equals button on your calculator, type in the x minus 1 quantity squared minus 2, you can graph it, and then you can see on the graph where it's dipping below the x-axis, and then you'll just need to find the x-intercepts, and it will do that for you as well. So you can use that as a tool also. All right, but anyway, that's it for section 2.3. And we'll be practicing these in class, and good luck with your quiz on this material. I won't ask you, I'll try not to ask you anything too hard on this stuff. So thank you, and I'll see you in class.